Hey guys, so for today, estimating means, lesson 8.3. If you would open up the 8.3 day one notes and also open up your formula sheet because I'm going to be flipping back and forth a lot to this. You will also need your textbook. There will be some things I need to show you in your textbook, so having that close by will be beneficial. All right, so let's begin. So we were going to have Oreos today. See, we got to the good part and now we have to do this virtually. Anyway, so for some reason the formatting got screwed up again. And number one said, what is the point estimate for the true mean? So we wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than what has been advertised. So we took 30 cookies and I calculated the mean weight at 11.1921. Oh, I have a visitor. See if y'all can see my visitor. Oh, can you say hi? He's going to make it hard to video, but anyway, sorry. Okay, bye again. So anyway, mean weight of Oreos, 11.9121 grams was what we found in our 30. Standard deviation of our sample, 0.0817 grams. We're going to make a 95% confidence interval. Now, the difference between 8.2 and 8.3 is we did proportions with the Hershey Kisses. We're now going to do mean with the weight of Oreos. So number one said, what is the point estimate for the true mean? So of course that is the 11.1921 grams. That's X bar. The population of interest is all of the Oreos ever produced. And the parameter is going to be mu, the true mean weight. The sample is our 30 Oreos, and our statistic is X bar, 11.192 grams. Again, we have to check the random condition so that we can generalize to the population as a whole, and it was met because I told you it was met right there, random sample of 30 cookies. The formula for calculating the standard deviation of the sampling distribution of X bar is on your formula sheet. So let me show you where that is. So if you go to your formula sheet, you're going back down to page 2, and where it says sampling distribution for means, here is your, that's where you'll find what you need in your formula sheet. So as we learned in chapter 7, these two formulas from chapter 7. All right. Okay, so there is the formula for calculating the standard deviation. And just like with proportions, we will not know our true standard deviation. If we knew our true standard deviation, we wouldn't need to write a confidence interval. We would have all the information we need. So we will be using our standard error, same way we did with proportions. All right, so the condition, again, is still the 10% condition. It must be met, so we can use this formula. And it is safe to assume that 30 is less than 10% of all the Oreos on the planet. So the standard error, which will take our sample standard deviation, divide by the square root of our sample size, is 0.0149. So if you look back at the top, the standard deviation was 0.0817 from the sample, divide by the square root of the sample size, 30. So again, we have to check to see if we can use a normal distribution. And yes, we can, because our central limit theorem that we learned in chapter 7 states that if the sample size is 30 or larger, the shape of the sampling distribution will be approximately normal. Since our sample is actually 30, the central limit theorem applies. Now, a lot of students get messed up between when to use large counts and when to do the central limit theorem. You will use large counts, NP greater than or equal to 10, N times 1 minus P greater than or equal to 10. You'll use large counts for proportions. You use the central limit theorem when you're dealing with means. So we now need to find the margin of error. We used Z star for proportions, but that's not going to be what we use when we are dealing with means. For a mean, we will use what's called T star as the critical value. So if you remember, a z-star yesterday was the number of standard deviations away from the mean. And for proportions, when we standardized using p hat instead of p, the new z, or the z-score we found, still followed the normal distribution. Well, something weird happens when we use the standard deviation from the sample when standardizing. We don't get a normally distributed standardized curve. We get something different. So we gave it a new name called t-star. This is where I need you to go into your textbook with me. If you will turn to page 505 in your textbook. If you will look at the top of page 505, page 504, that gives you a little more details about the t distribution and why we have to use it if you're interested. But on page 505, it says, I'm going to read the yellow box. Draw a simple random sample of size n from a large population that has a normal distribution with mean mu and standard deviation sigma. The statistic t equals x bar minus mu divided by the standard deviation of x divided by the square root of n is not going to follow a normal distribution. It's going to follow what's called a t distribution. And what I find very, very interesting about this t distribution is, go to the red box beside the yellow box. The t distribution and the t inference procedures were invented by William S. Gossett. Gossett worked for the Guinness Brewery, and his goal in life was to make better beer. He used his t procedures to find the best varieties of barleys and hops. Gossett's statistical work helped him become head brewer. Because Gossett published under the pen name Student, you will often see the t distribution called Student T in his honor. So what was happening was he was trying to make better beer. So he was standardizing his values of X bar from the mean, his sample mean. If he was finding, weight of the hops or weight of the barley or whatever you do when you're testing barley. So he noticed when he kept standardizing it, he was getting way more values outside of 3 standard deviations away from the mean. And we know from the empirical rule that shouldn't have happened. So he started noticing that the normal distribution didn't really apply when he calculated this new statistic using the same format that we used when we were calculating Z, the statistic minus the parameter divided by the standard deviation. And he was like, something's going on here. So through his investigation, this whole new branch of statistics kind of opened up, and it was all because of beer. So beer, you can thank for this t distribution. But anyway, so proportions, we will be using z star for our critical value. When we are writing a confidence interval for means, we will be using t star. So if you go back to that yellow box on page 505, we have to know the degrees of freedom in order for us to calculate t star. So in the yellow box, it says that the t distribution has degrees of freedom, which we'll use df to abbreviate, is the sample size minus 1. So to find t star for this confidence interval, so let's refresh, we've been talking a while, 95% confidence interval to estimate the true mean weight of an Oreo. So we had 30 Oreos, so the degrees of freedom is 30 minus 1, which is 29. So if we'll go to table B, so I'm going to go back to my formula sheet. I'm going to scroll all the way down to table B. Because if you'll notice, table A is z-scores. Table B is the distribution of critical values for T. Now, this is constructed a little differently. The probabilities are across the top. Now, if you'll remember, these are the probabilities to the right of T star. And then the degrees of freedom go down. So our degrees of freedom were 29 because we had 30 minus 1. And we're doing 95%. So if we think of 95%, there'll be 5% in the tails. If we shade the 95% in the middle. And then the 5% in the tails, we cut that in half, we get 0.025. So you'll go to 29 over to 0.25. There is your critical value, 2.045. And there's a picture of what I just told you. Okay, so there's a picture about the tail probabilities and why we use 0.025. So, and there is the picture, 2.045. So now let's calculate the margin of error using our T star and the standard error. So the margin of error is your critical value times your standard error, which we found in number 6. So this 2.045 that we just found from the table times 0.149 gives us the 0.035. That's our margin of error. So of course our confidence interval is the point estimate plus or minus your margin of error. So 11.1921 was the point estimate. That was our sample mean weight of the Oreos plus or minus the margin of error. And that gives us a confidence interval of 11.1616 to 11.2226. We are 95% confident that the interval from 11.16 to 11.22 grams captures the true mean weight of Oreos. So again, to draw your attention back to your formula sheet does not give you a specific detailed equation for how to calculate the confidence interval. All it gives us is the general structure of a confidence interval. So you have the structure right here, but you don't have the legit formula. So that's what this next question wants you to do, is write a specific formula using symbols and notation for a confidence interval for a sample mean, because that's what you're going to have to do on your AP exam. You're going to have to take the words and specifically write it. So your point estimate plus or minus your critical value T star times the standard error of the standard deviation, the standard error. So this is what you have to remember from the words. So you're going to have to take these words and know that if you're doing parameter, you'll use p hat for statistic. If you're doing mean, you'll use x bar. Your critical value for for proportions is z star. Your critical value for means is t star. And then your standard error of the statistic, you have those formulas on the next page. So you have everything you need. You just have to kind of piece it together. So look back at your interval, 11.1616 to 11.2226. According to Nabisco, an Oreo weighs 11.3 grams. Does our confidence interval provide convincing evidence that the true average weight is less than 11.3 grams? Well, based on our sample, our entire interval is less than 11.3 grams. So we can conclude that we have evidence that Nabisco may be telling us a fib, that the weight is 11.3, less than 11.3 from what they claimed. So to recap, what we have talked about is the conditions for constructing a confidence interval for mu. The random condition, the 10% condition, and the normal condition have to be met. Remember, random, so we can generalize, 10% condition, so we can use the standard deviation formula because independence will be met, then the normal condition. Now, with means, however, we have a little something different we have to talk about. So if you remember from chapter 7, if you are told the population, the original population, the population distribution, if you're told it's approximately normal, then the normal condition has been met. If you have no idea the shape of the population distribution, but you know your sample size is greater than or equal to 30, the central limit theorem tells us that we can proceed as if the sampling distribution was approximately normal. But what if it's not 30? So I need you to turn to page 512. Your T procedure using T star is, in statistics, is what's called robust. Robust means that it, and this definition is on page 511 if you would like to read it. An inference procedure is called robust if the probability calculations involved in that procedure remain fairly accurate when a condition for using the procedure is violated. So there are some scenarios under which we won't be able to verify the normal condition, but we'll still get to use this confidence interval procedure. So on page 512 in the yellow box, it says, if your sample size is less than 15, you can still use these T procedures if the data appear close to normal, roughly symmetric, single peak with no outliers. If the data are clearly skewed or if outliers are present, you can't use T. So when they say the data, you would take the 15 pieces of data that you have and you would do a dot plot or histogram or something, and you would look for skewness and outliers. If the sample size is at least 15, so between 15 and 30, you can use T procedures unless there is extreme skewness in your data or there's some outliers. And of course, if your sample size is greater than 30, the central limit theorem says that the normal condition has been met. So it gets a little tricky with the T distribution, but the good news is even if your sample size is small, there are certain scenarios where this normal condition can kind of be fudged over a little bit. So you need to know those three things on page 512. Your critical values, we're going to use T star for means, and the degrees of freedom are going to be sample size -1. You can use table B with degrees of freedom and your confidence interval. I think that should say confidence level. Always round down if degrees of freedom is not on the table. So if you go back to your formula sheet with me and we go down to the degrees of freedom, I want you to look at what happens. At 30, it stops giving us individual values. So we do have some limitations on your sheet, your formula sheet. So if you have to use your formula sheet, you're going to round down if degrees of freedom is not on your table. So if you find degrees of freedom between 30 and 40, round down to 30. But the good news is you can also use inverse T. So if you'll go to the same place you found inverse norm, second vars, you should see inverse T. Just remember that inverse T puts the area to the left, and then you put your degrees of freedom. And then you can use a calculator and you don't have to use the table, but my job, I have to show you both. So I would like for you to try the check your understanding. And again, the formatting is really goofy here. So don't look at mine, look at your notes. So try the check your understanding and then come back in a minute and see how you did. Okay, so were you able to use table B to do a 96% confidence interval based on a random sample of 22 observations? Did you get your T star at 2.189? Did you get for a 99% confidence interval? If you use the table, you got 2.660. If you used inverse T, you got 2.648. Remember, these are your critical values. These are your T stars. And then it says, Judy is interested in the reading level of a medical journal. She records the length of a random sample of 100 words. And then here is the histogram. So by looking at this, we want to see if the conditions have been met. So this kind of takes us back to that box on page 512 in your textbook. The random sample was used. It was stated in the problem. The 10% condition has been met since it's safe to assume there are more than 1,000 words in this medical journal, or 100 is less than 10% of all words in the journal. And since we took a random sample of 100 words, this number is greater than 30. So the central limit theorem does allow us to say the shape of the sampling distribution is approximately normal, even though when we graph the data, we see clearly right skewed. But because the sample size is large enough, we can proceed with our T star to construct our confidence interval. Now, if our sample size had been less than 30 and we saw a graph like this, we would not be able to do a confidence interval. We would have to increase our sample size, go back to the drawing board or something. All right, fellas.